then, we grow these materials in wide variety of substrates, wide variety of 2D materials. We grow it now on 4-inch wafers, and then we perform a plethora of characteristics, including AFM, XRD, XPS, Raman, PL, and then finally, we actually transfer these materials from the growth substrate onto our device fabrication substrate and make transistor devices with channel lengths ranging from all the way down to 100 nanometer to tens of micrometer, because we can use nanorithography tools which are available to us. And then we actually don't stop at making only a single device. We are actually trying to make integrated circuits. So we are actually going forward, not only one device or 10 devices, we are actually making 100,000 and even 10,000 and sometimes even 100,000 devices, and then trying to connect them and make these integrated circuits out of these 2D materials to really push the technology from lower TRL levels to a higher TRL levels. And here, when you are trying to make a technology out of this 2D material, you really need to characterize many, many devices, not just report your single champion device, which kind of gives you the highest mobility or highest on current. So we do a lot of benchmarking of our devices. We regularly measure, thousands of devices, and then we find out what is the statistical distribution in terms of their electrical and optoelectronic properties. And here what I'm showing is that, this is one of the studies that was reported, last year, actually earlier this year in Nature Communication. Sorry. Now, 2D materials, as you can see, they're primarily been N-type. Most of the exfoliated materials have shown N-type characteristics with some ambipolar characteristics from tungsten selenide or molybdenum telluride. But there has been really lack of P-type 2D materials. But now, with again, thanks to my wonderful colleagues who kind of keep going, wonderful materials, we have been able to also grow P-type 2D materials, which is nothing but vanadium doped WSE2. And you can clearly see that the MOS2 monolayer, which is large area grown, is primarily N-type device, while vanadium doped WSE2 is primarily a P-type device, because vanadium is a P-type dopant for WSE2. So now we have the capability of making both N-type and P-type channel material, which is very important for CMOS. The next thing is that our devices are not only just logic devices, but I could also program my devices. And that is something that is not allowed in a von Neumann architecture, as I was mentioning. Your logic and memory are separate. But in our devices, we are actually using a particular gate stack which can actually trap and detrap carriers. And these carriers can be either photo-generated or can be generated by electrical impulses. And what we can do is we can essentially write a state into my device, and if required, we can also erase that state. And here is an example. You can see that by applying negative voltages to the backgate stack, I can essentially transform my device from a low conductance state to a high conductance state. And this is nothing but essentially your neural networks where you store different weights. So I can simply have different conductance values in the same channel material just by programming it. And I can do the reverse by applying a positive voltage, where I essentially go from a high conductance state to the low conductance state. And once you put the device in a particular conductance state, it actually retains that information. That means it's a non-volatile memory device. And I could do it with both the NFET as well as for the PFET. So both my NFET and PFET are now programmable. Sorry. Now, with this programmable computing primitives, what I could do is I could actually connect them in series, and I could make inverters, I could make sigmoid neurons, I could make Gaussian neurons, and these devices can also be programmed. So I have now programmable primitives for this 2D material based transistors. Now, another important thing that I would also like to mention is that these 2D materials being monolayer, they're very photoactive. So therefore, they're responsive to light. And here you can see for different illumination intensities, I can get different photocurrent from the device. Another important aspect about the 2D material is that depending upon where you are actually doing this illumination, you can actually store that information. So let's say, for example, if the illumination was done under a positive gate bias where my device is in the on state, then post illumination, the transfer characteristic does not change. But if the illumination is done under negative bias condition, then you can see that after the illumination, the device actually retains that information. This is nothing but you create this photogenerated electron hole pairs, and these holes essentially get trapped into the underlying oxide, and that results in a threshold voltage shift in the device, and that results in a post illumination current, or something what you in optics society is very well known as the persistent photoconductivity. Now here the photoconductivity is actually gate tunable. So what you can use it for is some kind of a direct learning. So because your device is now becomes a machine vision with the capability of machine learning, because as you keep illuminating the device, you keep trapping more and more charges, and that changes the conductance of the device. And once you remove the illumination, the device actually remembers what illumination level it has seen previously. So your device acts like vision as well as learning. So here, for example, we illuminate an array of 9 devices using this particular illumination pattern, which is the letter T. And then what happened is that after a certain amount of time, the device conductance actually reflect this input information. So my device is able to learn from the optical information that is being seen. Again, another important aspect is that the persistent photoconductivity that we are seeing in this 2D material is gate tunable. So by just applying different gate biases, the amount of photo response in the device actually changes, because I simply enable different amount of trap states in my gate oxide. The advantage of that is I can now learn information in both low light, scotopic or high light condition. So let's say, for example, now I have an information which is actually have a very less contrast. By changing the gate voltage, I could learn the information similar to how I would be learning in a photopic condition or under bright light condition. So therefore, these kind of devices could be very good for night vision cameras, where the contrast is actually less, but your device can be tuned in order to essentially give you the same contrast what you would have gotten otherwise if it was a bright light condition. The other important aspect is my device is electrically programmable. So what I described just right now is the fact that my device is optically programmable. But at the same time, I can electrically program the device, which means that the information that is stored can be removed immediately, right? Because if you want to use your device as a vision sensor, right, then you also want to refresh it or reset it very quickly, right? And that can now be done by applying an electrical magnetic pulse of inverse polarity. So therefore, my device can not only learn, but it can also forget. And how fast or how late it forgets can be controlled by the magnitude of the electrical impulse, right? So therefore, in a device like this, you have the capability to program your responsivity as well as your response time. So both the responsivity and response time of your 2D material-based photodetectors are programmable, right? And that is something very unique about the device structure that we are using. Now, how does it make a big difference? Let's say, for example, you want to do something like an unsupervised learning, where you are in an environment, your sensor is deployed, and you want to essentially capture when there's a change in an event. So if you want to design event-based cameras, then based on the change in the event, your device should automatically capture the new information. If you do not have the forgetting capability, then the device will simply learn and never forget, right? If you introduce this forgetting capability, then you will see that, you know, my device learns this new information, and then when a new information comes, it can also relearn by forgetting the previous information, right? So this is kind of help us to do some kind of an unsupervised learning using our devices. Now, the next thing that I'm going to show you is that, so what I described till now is the fact that my device can do sensing, it can do programmability or computing, as well as it is a storage device, right? Now, using this, we have essentially developed a technology for collision avoidance. Because collision avoidance is actually very important for any autonomous vehicles or drones or robots. Now we are deriving the inspiration for this design from the animal world. In fact, looking at locust. So locusts move in a swarm, but what is very fascinating is that, they're actually very infamously known for wide-scale devastation of the agricultural field. But what is very spectacular about the locust is that in a swarm of locusts, there are millions of locusts which are spread over, let's say, a square kilometer, and they are flying. All of them are flying, but they never collide with each other. And that is because the vision system in the locust is actually very unique. In fact, it has a single neuron, which is called the lobular giant movement detector neuron, which can help this locust to avoid collision. So a single neuron can perform a very difficult computational task, a vision task, which is very difficult. Now, how does it do it? So let's say, for example, you have a looming object or an optical stimulus, which is essentially approaching the eye of the locust. So it actually projects an angle theta. And as the object comes closer and closer, the angular projection simply increases. Now, you can see that the locust has a neural network, which is very unique. It has two dendritic branches. So what it does, it takes the angular velocity of the moving object, which is the theta prime, and creates an excitatory response in one of the dendritic branches through a feed-forward neural network that exists from the photoreceptors in the eye of the locust. Now, the angular projection theta actually comes to a lateral inhibitory network, and using this red dendrites, it actually converts the excitatory information into an inhibitory response. So although the angle theta is increasing, the dendritic branch creates a response which is actually monotonically decreasing. Now what the LGMD neuron does, it actually multiplies these two responses and creates a non-monotonic profile. And because there is a non-monotonic profile, the firing frequency actually becomes maximum before the collision is going to take place. So this is a remarkable mechanism which is essentially showing that you are integrating computation with the vision sensor in order to perform difficult vision tasks like collision avoidance, and that too is done by a single neuron. Now earlier there has been a lot of mimicry of the entire neural network of the locust eye, and it uses like 34 transistors, 5 capacitors, a lot of vision sensors. So the system is very bulky and not really energy efficient. What we have done is we have used a single device, a single MOS2 based optoelectronic device in order to mimic the LGMD neuron. And the way we have done it is we have used the optoelectronic property of the MOS2 to create an excitatory response in the device. And at the same time, we have used the programming capability to create an inhibitory response. So let me show you how we have actually done this experiment. So here we have a toy car which is mounted with a LED, and it is approaching my vision sensor. So these are on collision course. So let's see what does the vision sensor experience when an object is on a collision course. You can clearly see the intensity of the light keeps increasing as the object approaches closer and closer. And that's kind of obvious, right? I mean, if two cars are far apart, then the intensity of the light that this sensor will get is very low, and at the collision it will become maximum. So if I expose my device to the same kind of visual stimulus, then of course what we'll see is that the photocurrent kind of keeps increasing monotonically. Now, depending upon how fast the object is approaching, you can see that the photoresponse of the device is also different. A faster moving object creates very early response, while a slower moving object creates a later response. And that's kind of expected, right? Depending upon the object speed, my response will be earlier or later. But this information alone is not good enough for your vision sensor to detect